Performed already the network analysis using the Hardy-Cross method, and now I would like to once again show the main parts of our study. So basically, you have a system like this, and the system will be, of course, different for you to do your projects. You have a source here, and water comes from this source with the main inlet pipe, which we call AG pipe, because source is A and the first junction is G. And then you have all other junctions like D, E, K, I, H, G, F. Sometimes you have some reservoirs over here in order to store some water. Sometimes you don't. So this is not a rule. You will all have different scheme or different drawings. So first things first, what you will do, you will write the coordinates, okay? You will write the coordinates in X, Y, and Z Cartesian coordinate system. Why you are writing these coordinates? Because in reality, every junction, every location has a coordinate, right? So, and also, it will help you to identify the length of pipes. If you just, I don't know, if you just subtract this value from this, you will see that the pipe length is 243 meters. Or you can do it in this way. It's based on the Cartesian coordinate system. So, if you notice the node H assumed to be the origin of the system. Let's have a look at the system again. H, it's on the very bottom left corner, so it's assumed as a 0, 0 location. Therefore, its X coordinate and Y coordinate are 0, and all other coordinates are based on our location H. Sometimes they are negative. Why? Because if they are out of the Cartesian coordinate system, like for example the source A, it is on the left side of this H, therefore its X coordinate must be negative, right? Therefore it is negative 30.5. And Z coordinate represents the height, the altitude of that location regarding a reference point, a reference line. And after that, you need to set the table 2. It is basically based on the demand. So NU represents the number of units. How many units you have in that area. Basically, you can assume these units as houses, okay? And average day unit demand, it means every unit consumes or requires for their daily activities that much water, okay? 4,315 liters per day. It looks quite huge, but actually it is not. Imagine that 5 people are living in a house, they are taking showers, they are washing their clothes, washing the dishes, watering their garden, cleaning their car, cleaning their houses, I don't know, even going to a toilet and pressing the flush counts. Therefore, if you consider all these activities, they are not, the value is not that huge. Number of junctions is 8. It's obvious if you just count this 1, 2, 3, 4, 5, 8. And maximum day factor. What was the maximum day factor? Does anyone remember? It is the ratio between something. Maximum day factor. It is the maximum water consumption. It is the ratio between maximum water consumption and the average water consumption, right? So when will be the maximum water consumption in a day, or in a week, in a month, if you assume daily consumption? When will be the maximum water consumption?
In the morning.
In the morning, right? People before going to work, before going to school, they are washing, they are taking showers, they are going to toilet, they are are preparing breakfast, etc. And also the maximum consumption can occur at the evening when people come back from their works, their schools, etc. And fire flow, it is the amount of reserved amount of flow in pipes in case of any fire incident. This amount of flow will be used, okay? And how do they use it? They install fire hydrants, and in these fire hydrants they can easily attach the hoses, and then they will try to extinguish the fire at the incident site. So they are all based on the population, based on the cultural activities, and also complexity of the city or the town. You must accept higher fire flow rate for Istanbul than any other small Turkish city, right? So it is basically based on how crowded the city is and what kind of activities are performed every day. And in table 3, you are explicitly stating the pipe parameters with its diameter, with its Hazen-Williams constant, and with its length. How do we know these Hazen-Williams constants? Are they always 130? No. So they are based on what? They are based on the material of the pipes. So it's given over here, and it will be always given to you, or as an engineer you will find out the Hazen-Williams coefficient of the pipes you will use, and it is not your duty to measure that value. When you order the pipes, in the technical documents it's already written. Of course you can also measure it by doing some experiments, but there is no need. Of course, you need to assign the positive directions, and universal way of doing it counterclockwise, okay? If it is counterclockwise, it means it is the positive direction. And now it is time to calculate the water demand in each junction. For this, you need to calculate the AD. It is the average day demand. Average day demand. How do you calculate it? You basically multiply NU, number of units, by Q. What is Q? It's over here. Average day unit demand. So how much water is demanded by units times number of units. So it means the average day demand in the whole system, whole town. So of course you can multiply 300 by 4,315 with your calculators, but if these values change, which of course they will change, you cannot calculate everything by your calculators, especially for the iterations in the next steps. Therefore, we are creating this Excel table, and even with this simple calculation, we use Excel to do it. So 300 units, this much liters, and this is your average day demand. And of course, we always write the units. Writing the units is the most important part. If you do not write the units, maybe you will get lower marks in the course, in this course, but in your future professional life, you will have quite bigger problems, okay? So do not, how to say it in English, restrain yourself writing the units. It's not a burden, it is a thing that will help you a lot. Anyway, average minute demand. How do we calculate the average minute demand? If you have the average day demand, if you divide it by the number of number of minutes in a day, you calculate the average minute demand. Okay? Because why? In one day there are 24 hours, every hour has 60 minutes. A maximum day demand, how it is calculated? You need to multiply the average minute demand by the MDF. What was the MDF? Maximum day factor, right? Here. So you multiply these two parameters to find out the maximum day demand. So here we assumed all junctions have the same demand, but in reality, they do not. Let's give again the same example from our campus. If you assume our campus as a town, what do you expect? The demand in hospital will be much higher than the demand in Starbucks, right? So it will never be this way. You cannot assume the junction demands are same, but in order to understand the background, in order to understand how to create this Excel table, we assume the demands are same at every junction, but in reality, maybe also in your project, it will not be the same. Therefore, if you assume all of them are same, you need to divide that maximum day demand by the number of junctions to calculate the demand per junction. So it means every junction in our system consumes, or not consumes, requires for its activities, daily activities, 197 liters per minute. So every minute in this junction, almost 200 liters of water is required every single minute. Okay? And after that, you jump into the next table to write the consumption in the nodes. So this is a bit more precise calculation because we have found 197, but if you just divide these numbers, you know, this is a number with digits, actually you find this, okay? So it's up to you how sensitive you are working regarding the digits. Anyway, so in each junction you have the same amount of demand, but at QF, I mean F junction, has a little bit higher, maybe not a little bit, actually quite higher demand. Why? Because in this junction, you have a fire hydrant. You know what fire hydrant is, right?
Yes.
That red thing on the street. In computer games, if you hit by car, it explodes, etc. So you add that fire flow rate you found somewhere, where we found it, yeah. Actually, we did not find it, but it is given. You add that fire flow rate into your regular consumption or regular demand, and you obtain this value. And if you want to find out what is the demand in the whole system, you just add all of these values together to find the system demand. MDD plus FF. What is MDD? Maximum day demand. And FF is the fire flow. How do we find the maximum day demand? It's obviously here. So this plus this will give you the system demand. Your whole system demands that much water. And once again, we write the demand flow rates at junctions. So maybe I should zoom it a little bit more. So in this junction, water comes from source A, then it is distributed into two parts, right? In this, it's branched in this pipe and also into this pipe. But also it has this amount of flow that goes into the system. Actually, it means it goes into the units that are located at junction G. Okay? So nobody is here actually. They are already on the junction G, but in order to show it explicitly, we draw it like this, as if there are some people over here and they are drawing that much water, okay? So we write the same amount of water drawing at every junction, as you see. At every junction, we have assumed the same amount of demand. Actually, we assumed over here, like the all junctions have the same demand. And how did we find that value? We divided the maximum day demand with the number of junctions. Okay? But of course it was an assumption, and as I said, in reality there is no such assumption. Okay? Why? Just remember the hospital and Starbucks example in our campus. Anyway, So our flow is distributed in these two directions, then it will go in this way. Some of them will go into system, some of them will go out, etc., etc. They will follow their ways, and then they will end at F, right? So here, this can be a source, or it's free to not have any source over here. This is just an example. We even didn't took it into consideration. So you can, if you want, just forget about this. The main idea is where it ends, where it is completely consumed, okay? So what we will do next, we wrote everything over here, and we need to tabulate it. How do we do it? Using this table 5. So assign flows and calculated values. When you look at it in this way, it looks intimidating and it's quite scary, like as if we are doing quite complex things. But actually we are not. Let's go back to our drawing again. And as an instinct, what do we say? This flow is the summation of these two, right? The last flow at location F is the summation of this and also this. So we can say, let's divide our last flow into two. Half of them is here, half of them is here, right? So QGF, which means the pi that starts from G to F, and it represents the flow that comes from G to F. Therefore, in this table, we have said, let QGF is the half of Q at location F. So we should know the difference. We should know the difference in notation here. QF and QGF. QF means the flow that is in junction F. Okay? So it goes to the units at junction F. But if we say QGF, it means flow comes from joint G and goes towards joint F. Okay? So in this case, if our QF is 6,821.1, how did we find it? We just added F5 flow rate with the QF. You remember it. We just divided into 2 and we found this value, QGF. Once again, we are pretending like this flow is the summation of this and this, which actually it is. But we assume half of them is here and half of them is here. These initial assumptions will later automatically balance itself. Therefore, we are doing these balancing procedures, iterations, etc. So let's go back once again. So we now say the flow rate from location G to F is this. Now let's try to do some balance in node F. Okay? Let's go to node F. We are here, node F. And of course, we draw it once again with some red numbers on it. Eventually, we found these red numbers, but in the beginning, none of these are known. Okay? None of these parameters are known. As we find, we start writing them. Okay? As you know, we divided this into 2, and we wrote these numbers here. They were not here before, so do not get confused when you see these numbers, and don't ask me, how did we find this? We find it one by one, okay? Initially, we don't know it. Once again, we divide this into 2, and we found this. Now, balancing at where we were doing the balancing, at F, right? So, we only know this, and of course, if you say this plus this will be this, and if you found this as half of this will be the other half, right? But let's make it more scientific, and the balance in node F is this. QEF, which is the flow in this pipe, is QF minus QGF, right? It is quite obvious, but it is important to follow a particular procedure, okay? Any problem until now? It's clear, right? Is it clear? Okay. And we always write the units over here. So F is over Now, before we balance at E, we do some little assumption here again. We say, let QKE equals to QEF. What does it mean? KE and EF are set. We say, let's say the amount of flow in this pipe will be equal to this pipe, and this amount of flow goes out, and it is directly coming from this pipe. Okay? Imagine that this flow comes in this way, and it automatically goes out. Therefore, the flow in this pipe will be equal to flow in this pipe. And again, it is my way of approximation, it is my way of assumption. If you want, just write here 30, and then if it is 30, 196.7 goes out here. So what will be the remaining one here, considering this one? It will be a little bit more difficult. Therefore, I suggest you an assumption in this way. Imagine that all the water that goes into joint E comes from this pipe, and therefore the flow that goes in this pipe is coming from this pipe. So it will be easier for you to write the values. You will automatically write 3,400, 3,400, 196, 196, without considering any other thing. But of course, the scientific way of writing it is this: let QKE equals to QEF, and therefore QKE equals to this. And also another assumption, again, I am telling you, you can do any kind of assumption as you wish, as long as you satisfy the complete balance. Okay? For example, I said here, let 50 liters per minute of flow goes in this pipe. If you are not satisfied, go for it. Just say 30, 10. If you want, say 1. Just 1 liter goes in this pipe. It's up to you. Because eventually, everything will be same. The assumption you do and the assumption I do will come to the same point. Okay? It's all up to you. If you want, you can write here 100. It doesn't matter. It's all up to you. I personally prefer 50. And if it is 50, and if this is 300, 3,410, and if you have also 196, what will be this pipe? This plus this plus this and this, right? So you need to write this, everything we see over here, in an Excel format. Like how? Like this. We assume let Q kg 50. If Q kg 50, then in node E, you do a balancing like this. Let's come back again, E. What do you have at E? This one enters positive, or let's say this one enters on the left-hand side of the equilibrium. This one is positive, it enters into E. Also at the left-hand side of the equilibrium. This one goes out, and this one goes up. So these two are on the right-hand side of the equilibrium, and these two are on the left-hand side of the equilibrium for calculating the junction E, right? Are you still tracking, or you already passed away? Okay, once again, junction E, we are trying to create an equilibrium, so we put our equal sign. This and this enters into system, therefore they are on the left-hand side. This and this goes out of the system, therefore they are on the right-hand side, or at the right-hand side. In more scientific way, it is written like this. Okay? You can take a picture if you want. So in this way, how do we calculate the QDE? We just send the other thing on the right. We write all the values we know, and we find the QDE value. I know you can do all of them in a second using the calculator, but when the parameters change, it will take more time than doing it in the Excel. So balancing in node D, how we will do balance at node D? This enters into system, this exits, and this exits. Therefore, these two will be equal to this, and you will be finding 393 by using this simple Excel formula. And at G you also do some balance. I'm going a little bit faster at K, at H, at I, at G. So basically you know what to do and you need to write them in tables as you do over here. And as you see, they are in different colors because later we will be using them, okay? Maybe we can have a look at the balance in node G. It's a little bit different. Let's have a look at node G. We are here, right? So what we have this that goes out the G, this that goes out the G, this that goes out of the G. So the flow rate that enters into G from the source will be the summation of this, this, and this. And we have written everything over here, okay? Now, we need to convert everything into cubic meters, right? Because we like to work with cubic meters. And for each loop, we wrote everything in cubic meters. And in table 7, we are now getting into some business. In table 7, we wrote the flow rates according to their assumptions. Which assumptions? Direction assumptions. As you see, even though we wrote here without any signs, they are all positive here, we wrote them with the signs. So as you see, they are negative, they are negative, they are negative. So if you are smart enough, which I know you are very, if you would like to not show every step, you can directly write here with negatives. It's up to you. Okay? But I would like to show everything in a separate way. Therefore, I show the negatives in another table. Okay? And also, it is better to write the flow rates at every 5 after you calculate these two values. Okay? It is better to write on it every two values. Even though they are negative, their directions are not changed. It is very important. Do not change the direction and write negative at the same time. Either change the direction and write positive, or do not change direction and write negative. Okay? Same as before in the previous term. Now, our famous Thaysen-Williams equation has arrived for the velocity, which we will use later. For now, the most important one is the H, the headless one. So this A, B, C, D actually shows how they are modified to the last place. So therefore, I suggest you to just look at some basic formula. For example, this one is very important for you. Equation E, in order to calculate R. Okay? Why it is important to calculate the R? Because later you will be calculating the head loss with this formula. So you don't need maybe these two. You don't need maybe these two, but you definitely need these two. So for those people who haven't taken pictures until now, please take some pictures. I see there are some people using two phones at the same time. Okay. So R and HF, which is equation E and F, are the ones that you will be working with most of the time. Okay? And there are also some others, but we will get to them later. So, what we did, we now know some of the equations, and we will do some iterations. First of all, friends, what we will do, we will calculate the main inlet pipe parameters, because it is something separate. It will not go into iterations, okay? Why? Because it is separate, as you know, from the drawing. Where is the drawing? Yeah, it is separate, this part. So we will calculate this part first. Basically, we will apply the formula. So we write the diameter of this pipe it's very nice that we have the same diameters for each pipe, but maybe we will not in the future, who knows. So length, so calculating the R of it. Maybe it is the part that requires the most attention. How do we calculate the R? To calculate R, you need to know which parameters? L and D, right? So L and D is given here. Maybe this is not the most attention need part, but anyway. So you just write all the parameters. Basically, you create an Excel formula over here, and it uses this, and this, and you calculate this. And after that, you have a Q value, right? And you need to calculate the H value. So this is the most attention required part. So how do you calculate it? In order to calculate the H, you need to be sure about the sign of the flow rate. Our flow rate here is positive, obviously, it comes from reservoir. Therefore, using this if condition will be quite easy for you. You will just follow the formula as it is, which is your formula over here. You will multiply R by Q, but of course you will take the 1.85 power of the Q. That's it. Okay? And also you should calculate the capital R with this formula. And how do you do it? You just divide the you just divide the head loss by flow rate, and you multiply it by 1.85, considering its absolute value. The difficult part is here.
What was the big R?
Big R is this. You know the ratio between summations? Where is the ratio between summations? Let me find it. This R is this. Later you will calculate all R values to perform this formula. In the previous term, you remember that you were calculating delta Q with this formula. Minus ratio KQ squared, summation of KQ squares, divided by 2 times summation of KQ absolute. This was your delta Q, right? So here, this part is some kind of summation of QK absolute. Okay? But here your formula is this, and which we call as R. It's not the hydraulic radius that you have seen in hydraulics. It is different. If you want, instead of R, write here your name. It doesn't matter. Okay? So, here we have the junction names, diameters, Eisenhower coefficients, length, and now it's time to calculate R. How we were calculating the R, here is the formula. You calculate all the R values, and you know that if it is E means 10 power something. You are already almost engineers. So Q values are from the table. Which table? Table 7. This table. These are your Q values. So you consider if they are negative or positive from this table, and in this table you write them, sorry, where we are, yes, you write them by considering their signs. If they are negative, you will write them with negatives. If they are positive, you will write them with positives. Anyway, after that, here you will use the condition. What condition? If condition. For this, if your Q value is positive, which is positive over here, you directly, friends, use it as it is, which means you multiply R by Q, but of course you are taking the 1.85 power of Q before you multiply it by R, and your Q will always be in the absolute, okay? When you take the 1.85, you always put them in absolutes, because the 1.85 power of this will be negative, and we don't want this, okay? It should be in positive. And you find the h value. But for this one, if it is negative, while multiplying it with r, you are multiplying it also by -1, okay? Of course, this will be again in absolute, but you will be multiplying this value by -1 first, then you multiply these two by taking first the 1.85 power of the cube, and you find the h values. And later you find the r values, then you know how to do it. Where was it? We did somewhere, yeah. This is your r value, and you write all of them here. You take the summation of them, summation of h and summation of r over here. Why? In order to calculate the delta q. How delta q is calculated? Dividing the summation of h by the summation of r's, okay? And here you find the delta q value. As you see, as a successful engineering candidate, you tell yourself that delta q value is not that good, not good enough, so I need to continue the iterations. And of course, this is for only one loop. You do the same things for other loops simultaneously, okay? And now it is time to find out the adjacent cube, which means the next cube. When I say adjacent, it doesn't mean one of them is here, the other one is here. No, the next one I see. I mean next cube. So what you do over here, you just take the previous, sorry, we are here. You just take the previous cube. Sorry, friends. Hello. We calculated Q and delta Q, and what we do, we just add these things together. Q from here, delta Q from here, and we find the new Q value, like this. Any questions so far? Okay, so after that you do the same things, friends. Nothing is different. You do the same things until where? Q adjacent. Yes, from now on, you will take the new Q as the Q adjacent. Because why? You calculated, first you had one Q. Then you found the delta Q, and you found a new Q adjacent. Right? So in this way, you completed your first iteration. That Q adjacent is from delta Q plus Q. Now, look, let me do it in this way. That Q adjacent is the summation of this and this. After you find Q adjacent, it means you have completed your first iteration and now you are in the second iteration. So you write the new Q's in this way, and you have HI again. You do the same value, you find a delta Q. It's again okay, but not good enough for us. You go into the next iteration, next Q adjacent, and you continue in this way. And then you realize that's enough. But if not enough for you, you can go further. That's why I showed all other parameters. Yes?
Why two of them is, one of them is green and one of them is blue?
Yes. In order to double check if we are doing our calculations correct or not. Why? Actually, not one of them is green, but none of them is blue. Actually, this one is green, this one is green also. And what do we know? They are shared pipes in the loop. Let's go back to loop and see. Look, that KE pipe is both a member of this loop and also the member of this loop, right? So if it flows from left to right, it is negative for this loop, but if it is again flows left to right, it is positive for this loop. Therefore, for the first loop, it must be negative. For the last loop, it should be positive, but the values must be same, right? So in this iteration table, we also show it. Look, minus, positive, and positive and minus. The values are same, but the signs are different. Even after 12 iterations, their values are still same. Look, their values are still same, but their signs are different. So even after 12 iteration, if we still see the values are same, but signs are different, then we congratulate ourselves, which means we are doing iterations properly. If after 5 iterations or 6 iterations, the numbers are not same, that means you are doing something wrong. Okay? Signs will definitely be different because of the counterclockwise direction. But the values, even after 5,000 iterations, must be same. Okay? You understand?
Hocam şu sonda ne eklemişsiniz? Çıkarmışsınız pardon.
Nasıl? Which one?
Eksi AZ 207 nerede? AZ 207.
Which one are you talking about? This one?
Yes, in the formula AZ 207 there was.
This.
That's
Because I trust myself a lot, therefore I even take this delta Q into consideration. Like even the smallest variation does not affect my flow rate.
but should we take that one also?
If you are satisfied, you don't.
I didn't take it because of that my answers are different.
No, look, just focus on maybe the first 2 iterations, and that's enough for you. You calculate the Q,
Yes.
right, from the previous adjacent one. You calculate delta Q, how? H over R, and if you are okay with that delta Q, then it's okay.
But at the third one we need, like in the adjacent one.
Here,
Yes.
no, we just
Yes.
added the 2 previous one.
In the third one we should be
So in the third one, what do we have? We have these 2 parameters. We take Q and delta Q from the second
Yes.
iteration.
Yes.
It's always like this.
Not in the third one. Third one mean at the columns.
Third column, this column,
No. At the second iteration,
yes.
yellow, green one.
At the second iteration, this one.
Yes.
Okay, what it is? Look, what it is?
Only
What
the-
parameters you have? I207. I207 is this previous Q, right?
Yes.
L207, which is delta Q.
Delta Q.
And what is L21218?
The other delta Q. Okay.
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 So you perform all the delta Qs, etc. and all the iterations. Now it's time to find out the pressure losses per kilometer. Again, we have our lonely pipe over here, the main inlet pipe. We have the diameter C, L, R, Q, H values. We can easily obtain. I don't need to explain it again, I guess, because you already know how to calculate them. The only main difference here is in kilometer basis, what we do, we just divide the head loss into the letters, into the meters in total length to find out how much head loss we have for 1 meter. And after that, we multiply it by 1000 to find out its equivalent in terms of kilometers. And now we know that at 12th iteration we have completed our iteration process. Therefore, I just wrote the 12th iteration. Again, it is my way of creating tables. You can create in a way you want. And what we did over here, we calculated the head loss in a previous way, in a similar way. We divided head by the total length to find out how much head we lose in 1 meter, and after that we multiply it by 1000 to find out how much head we lose in 1 kilometer, because mostly these calculations are performed in kilometers, or we have some kind of evaluation process considering the kilometers, because nobody will say from here to Beşiktaş it is 11,000 meters. Nobody says this. Everybody says it's 11 kilometers from here to Beşiktaş, or 25 kilometers from here to Kadıköy, right?
Right.
Okay. And we would like to find out the pipe velocities. How do we find it? It is quite difficult. After you find the Q values, you divide the area, pi b square over 4, to find out the velocities. What will be the velocity in pipe? Because it is also very important. We see some negative velocities. It means we experience backflows in the system. Backflows. Imagine that you are installing a garden hose into the fire truck. The flow will not go into that fire truck. Of course it will explode, but let's say it won't. So you imagine some flow will go back because of that flow rate. So in these pipes we expect to have negative flow velocities, which means we are having flows instead of going in the designated direction, they are going back. And from now on, everything you create is just resembles what kind of engineer you are. If you would like to show everything in a compact way again and again or not. So show it or don't show it, it's up to you. We have already shown them. So after that, I will not evaluate any of your work because I will just check if you have found the velocities and also the flow rates properly or not. After that, maybe I just wrote by myself, maybe I copied from somewhere else to check something in the past, I don't remember. So after you find the velocities and flow rate, you are good to go. Okay? That's it. So this is how to balance a network using Hardy-Cross method with the approximation of Hazen-Williams equation. I knew we'll do some similar things for different networks, and after that we will once again have a look at our EPANet software once we have just learned how to click some buttons randomly, and after that we are planning to finish this term. We will compare the results that we obtained from the Excel file we have developed and also with the results we obtained from the EPANet software. Okay? So basically EPANet software does the same thing with this, but it's more visual and you don't need to worry about anything like you do here. It will handle automatically. So you will be able to solve quite complex networks in a quite cost-effective duration. Okay? Any questions? Okay.
Hocam,
Yes.
can you show a general view on the file again? Just a quick view from the beginning.
Quick view from the beginning.
Yeah.
So you want me to go scroll down quite slow like this, so you can record everything.
Yes, exactly.
Okay.
There is details here in the equation. Equation part.
Like this. Which
Yeah,
one
that's
would you
better.
like to see?
There is the equation part. It will complicated a little bit. There is a lot of details. Yeah.
Complicated, yes.
There is a lot of details.
Look, just learn these two equations.
Mm-hmm.
Okay.
Okay.
If you want, I can do this. Just learn these two equations. Don't memorize, learn. And also learn these questions. create your if condition. What else? That's it.
This. Right. Thank you, Hocam.
Table 9. What is table 9? Yes. I haven't studied on it.